Hi guys again. So today we are going to be having a little look at more on using orders of reaction. So previously we looked at what orders of reaction were. The fact that zero order means that the concentration of that reactant has no impact on the rate of reaction. First order means that it's directly proportional. And then the second order means that it affects it by the square of the change of the concentration. And we had a little look at how to use some of that information from a couple of different sorts of examples. So there's a couple of little bit more bits to that. Then you can see hopefully at the bottom of this that we're going to have a look at multi-step reactions and determining the rate determining step. We'll have a little look at that in a few minutes. Once we've done all of this, I'm going to set you some questions about all of this rate stuff that we've done so far. There is one more major bit about rates, which we've not come to yet, which is called the Arrhenius equation. Don't worry, I won't give you any questions on that, but we will cover that in some upcoming videos. So let's crack on. So previously, we had a look at concentration time graphs. We had our zero order is a straight line with a certain gradient. And of course, we know that rate is concentration divided by time, so we can easily work out the rate of that reaction based on just working out the gradient of that straight line. We then had our first order, and we looked at a couple of bits of information. We wanted to remember we wanted to have the rate at time equals 0, so at the very start of the reaction. And we also had to look at how we could work out the rate at various points. So remember that this was drawing a tangent from this, and the fact that there are a couple of ways that we can work out the half-life from this graph. That we can use this graph to work out k. One of those is to work out the half-life, which remember for the first order graph will be constant. For the zero order it will be decreasing, for the second order it will be increasing. And to work that out we do the natural log of 2 divided by whatever the half-life is. That will allow you to calculate what k is nice and quickly. And then we have our second order graph, which sort of decreases faster than the first order graph, but then sort of plateaus out. Okay, we've not really looked at ways of working out k from that. Okay, but we have a second type of graph. The first was concentration against time. This is rate against concentration. So you need to be familiar with both and identify them correctly. So for our zero order, we said that because it's a straight line, the rate is not affected by the concentration in any way, shape, or form. Therefore, the rate is constant at whatever value it is. I've just arbitrarily picked up at the top. Okay. For the first order, we said that rate is directly proportional to concentration, so it needs to be a straight line through the origin. Now, if they ever ask you in an exam to draw a line of best fit and stipulate that it's a straight line through the origin, that tells you straight away that it's a first order graph. Okay, they'll either be a horizontal line, or they will start from the origin in one of the two ways. Because of course, if the concentration of something is 0 and it affects it, then the rate is going to be 0. Okay, and second order this time sort of is increasing, because of course it's increasing at the square of the concentration. So this is again one of my last year's lot said that it's useful to remember that zero order goes first order goes and then second order goes sound effects apparently help sometimes. Okay. There is one more situation where I wanted to talk about calculating k. Now the previous ones were from the concentration time graph. This is from the rate concentration. Okay, so if we had a reaction that was first order, the rate would be equal to the rate constant multiplied by the concentration of whatever our reactant was, A in this case. If we rearrange that, and you'll have to excuse the capitalization, which definitely should not be a capital K there, the rate constant would be equal to the rate divided by the concentration of our reactant. If we think about this line, the gradient for this straight line is the change in x divided by the change in y. The change in x is change in rate, change in concentration along the bottom. Therefore, if we were given this graph, if we worked out the gradient for this graph, we would have worked out the value for k. Okay. One thing to be really careful is, of course, if they've given that the rate is something like times 10 to the minus 3, or the concentrations are all concentrations times 10 to the minus 3 or 4 or whatever, that's really important, and you need to include that in your calculations because that's a really common place that people end up going wrong. Okay, so we need to have a little look at a thing called the rate determining step. So up till now we've just talked about how the concentrations of different things affect the rates of reaction, and how to calculate either those concentrations or the rates that they affect. Okay, we know from our mechanisms that we've looked at that most reactions don't all happen in one go. Especially if we've got a lot of reactants, that's really unlikely. Okay, and if we've got several steps, one of those steps is going to slow us down, and that's whichever is the slowest step. If you imagine that you're walking through, I don't know, corridor in school, and it's single file, you can only walk at the speed of the slowest person. Everyone ahead of that slowest person will have walked off way ahead of them. Everyone else behind them will be backed up. You can only go as fast as the slowest step in our reaction. Okay. So if we have a little back to radical chemistry, then if, say, for example, the initiation step was our slowest step, that would be the rate determining step. That would decide how fast our overall reaction is, because everything else is faster than it. And we're basically sort of talking about the slow step being actually slow, and then everything else effectively being instant. Okay, and this is actually linked to the rate equation. Okay, so we can use the rate equation to work out rate determining steps. We can use rate determining steps to work out rate equations. Okay, so we hopefully remember that the rate equation is talking about how the concentrations of various different things affect different the rate in different ways. Okay. Now, the rate equation indicates the molecules that are involved in the rate determining step, and the order to which they are tells you how many are involved. Okay, so if we have one molecule involved of some substance, then it will be first order in the rate equation. If there were two of them involved in the rate determining step, it would be second order. Okay. If there are none involved in the rate determining step, then while it's involved in our reaction, it's not in the rate determining step. So to look at an example, we have chlorine radicals depleting ozone. Yeah, so remember this was our propagation steps. Okay, it turns out that the chlorine radical reacting with ozone is, in the first step, is the slow step. That makes that step the rate determining step. As far as we're concerned, the second step is instantaneous. Okay. Now, if we have a little look at that, we can hopefully see that we've got one chlorine radical involved and one molecule of ozone. Okay, those are the only items that are in our slow step. Those are going to turn up in our rate determining step, in our rate equation, in those same proportions. So it turns out that the rate equation for the reaction of chlorine radicals with ozone is that rate is equal to the rate constant multiplied by the concentration of the chlorine radical multiplied by the concentration of our ozone. Okay, and you will notice that there was only one of these. This is first order. Because it's first order, we don't need to put 1 because any number to the power 1 is itself, so we don't need to bother with the 1 there. And similarly, we've got 1 here and we've got 1 there. Okay, let's get rid of that. Alternatively, instead of using the mechanism to tell us the rate equation, which is what we've used there, we can use the rate equation to work out a possible mechanism, or to pick between two. Okay, so for the reaction of 2-bromo-2-methyl propane with hydroxide ions, there are two options. Either we can look at the reaction like we've got here, which is the mechanism that we considered, where we would have, and I'll do it with this pen, of course I will actually put the negative charge there instead of over there. We would have had a partial positive charge here, a partial negative charge here. Our electron pair would have been donated in there, and this would have broken off, and we would have ended up with bromide ion being left behind. I know that my arrows aren't very good. You'll have to excuse the fact that I was drawing over the mouse. Okay, let's just neaten that up a little bit so that it's more obviously pointing at the carbon instead of just underneath it. So that's one step. Alternatively, we can actually have a two-step mechanism where the bromide ion is lost first, and of course here this would actually be reasonably likely because we're forming a tertiary carbocation. So that intermediate here, this thing, which isn't going to hang around for very long, is actually pretty stable. Okay, and then of course our tertiary carbocation can then react with the hydroxide ion and form our 2-hydroxy-2-methyl propane. Okay, to work out which is which, we would need to look at the rate equation. And the rate equation for this is that the rate is equal to the rate constant multiplied by the concentration of our 2-bromo-2-methyl propane. That means that that's the only molecule involved in the rate determining step. Okay, that means that our reaction is this one over here. And this tells me that step number 1 is the slow step, and this is the only reactant in our slow step, and that is the only thing that is in our rate equation. If this mechanism were correct, we would also have to have the concentration of hydroxide ions. But we don't. So it's not that. It has to be our reaction on the right hand side, our two-step reaction in there. Of course, if we have a reaction which is just one step, then that one step is the slowest, and whatever is in that one step is in our rate equation. So that's not very interesting. Okay. What probably is most likely going to turn up is they will probably ask you to predict a mechanism, though. And they probably will ask you more complicated than this. And it will have to be at least a two-step mechanism. If they give you more than 2 steps, they normally give you at least some scaffolding towards that. And I'll give you some examples of these sorts of questions in my little pack that I'm going to give you. Okay. So, proposing a mechanism. Let's say we had our reaction at the top of nitrogen dioxide reacting with fluorine. Our rate equation is nitrogen dioxide and fluorine, both first order. That means that, let me just use the highlighter, that means that this reaction up here, step number 1, is our slow step, has to be our slow step, because if the second step was our fast step, then everything would turn up in it. And I know that it's got to be NO2 and F2, because those were the substances in my rate equation. So we have that, and remember that this is technically to the power 1, but we don't have to put power 1, and this is also to the power 1. So we've got 1 nitrogen dioxide, 1 fluorine here. Okay, that's going to produce something. We don't necessarily know what that is, but we have to propose something that's reasonable. And they give you a lot of leeway. The most important thing is that your your two steps of your mechanism end up adding up to whatever it is in total. So we'll have some sort of intermediate. That means that our intermediate here has to react, and we're going to have to form our two lots of NO2F. Now, it could be that part of that happens up here and part of that happens down here, but what we need to make sure is that our intermediates cancel, so that when we add up and cancel everything out, we end up with two lots of Na2 and F2 and two lots of NO2F. Okay, I'm just going to swap on a bit of paper because I think it's easier on a bit of paper, and hopefully this makes a little bit of sense, and then I will also put up some questions for you. So we're just going to swap now. Okay, so we said that this was our reaction and this was our rate equation, letting us know that we needed to start with NO2 plus F2, and that we're going to have NO2 there at some point. So this is step 1, this is step 2. Step 1, of course, is our rate determining step, has to be because it's the first one. Okay, we need to propose something that this is going to produce. So we could say, let's say NO2F plus F. That would be reasonable. This would then be our intermediate, and we're going to do NO2F, reactionary. So that gives us NO2F. That would be reasonable. Probably going to have a negative charge on those. Or we could do radical, in fact. Who cares? That would be reasonable, because if we add those up, we have NO2 plus F2 going to NO2F plus F, NO2 plus F goes to NO2F. If we add up things, we now have 2NO2 plus F2 plus F goes to 2NO2F plus F, or we can get rid of those, and that leaves us, that now leaves us here. If I move that up a little bit, might be able to see a little bit more. That now leaves us with the reaction that we started with, so that would be perfectly reasonable. Alternatively, we could, if that's still our information, we could have had NO2 plus F2 going to NO2F2. We remember, of course, that we had to have a molecule of NO2 here, because we've got 2 up there, and that would then react with our NO2F2 to produce 2 lots of Na2F. If we add up everything, we've got NO2 plus F2 plus NO2 plus NO2F2 to NO2F2 plus 2NO2F. If we cancel out the things that appear on the same on both sides, we get that, and we do indeed have our overall equation back, looking like that. Okay, the first one is actually the true one, but from what you've been given, that's a reasonable intermediate, so you could do that so long as your intermediates cancel out and you end up with the right overall equation. It doesn't matter. Okay, if they were to give you a 3-step reaction, we could have 1, 2, 3. We could have either step 1 as being the rate determining step, or more likely we'd have step 2, and then we would need to have a look at what the reactants were in step 1 and in step 2, as those should be what's in our rate equation. Okay, there will be an example that looks at that in the question paper that I give you. I want you to have a go at that and I will put out a video going through all of that for you. Okay, and I'll give you the mark scheme as well. Okay. Hopefully today made sense. I know that I've not asked you to do a whole lot, but I'm expecting the questions that I'm going to give you will take you a fair while. Okay, bye guys.